Hello, hello. It's astronomy time again. We are live with Dr. Doug Leonard of San Diego State University. Our talk tonight is going to be, so just when will Betelgeuse explode? Um, sorry, some technical difficulties here. Our speaker, Doug Leonard, is an associate professor of astronomy at San Diego State University. He received his BA in astronomy and astrophysics from the University of Pennsylvania and his MS and PhD in astrophysics from the University of California, Berkeley. His publications include over 100 articles in the technical literature. A passionate science educator, his latest endeavors include work on several BBC Horizon and Science Channel videos on black holes, cosmology, and the death of stars. And with that, here's our presenter, Dr. Doug Leonard.
Hi, everybody. It's really wonderful to be here, and I want to thank United Astronomy Clubs of New Jersey for asking me to give you this talk as part of your winter virtual series. And I would be remiss if I also didn't give a shout out to my big brother right there, Eric, who's an esteemed member of one of your member organizations and twisted my arm into giving this talk. No, he didn't have to twist my arm. I was asking to do it. This obviously was a picture from quite a while ago. I, of course, am now old enough to have my own little and big brothers seen here getting to view something at ages 5 and 8 that I had to wait till I was 49 to see. And I am going to bet that many of you know exactly what we were viewing from atop Snow King Mountain in Jackson Hole, Wyoming 3 years ago. If you don't know what we were reviewing, you better be marking your calendars for April 8, 2024, because that is when the next great total solar eclipse visits North America. Book your reservations now for Dallas or Indianapolis. Or I noticed if they're not to your liking, I see that if you figure out how to stick around until May 1st, 2079, you can just look out your own window from most places in New Jersey, and you'll see a total solar eclipse without having to go anywhere. At that point, probably visiting Indianapolis isn't sounding so bad. Anyway, lifelong memories from that event. My kids even got to meet an astronaut. But for me, one of the more profound discoveries I made, in addition to just seeing how neat a total solar eclipse was to actually be able to see and share something astronomical, see it with my own eyes, and share it with my kids and with other people. And the reason that was kind of revelatory is that just about everything I'd actually studied up to that point required really large telescopes to collect all the faint light from very remote objects that I was trying to study. The kind of data that I needed to uncover the secrets of exploding stars like supernovae, all done after the star had exploded. This is a typical kind of talk that I give on my research. But it was really neat just being able to see something. And I thought to myself, wouldn't it be fun to actually study something where I could just go outside and point at the object of interest and say, right there is Betelgeuse, and that's what I study. So it was about a year after the total solar eclipse that I joined an international team of astronomers, affectionately known as the Mob, who are singularly interested in studying probably the most famous star in the entire sky, Betelgeuse. It's the bright, distinctly red star that serves to demarcate the right shoulder of the mighty hunter, Betelgeuse. I can even see a hunter in this pattern of stars, and I generally don't see any of these things. So once you know where to look, it's hard not to see it. And this time of year, Betelgeuse is up all night. So you can the next clear night in New Jersey, just go out any time of night and look for the bright red star in the shoulder of Orion. That's Betelgeuse. You'd think it would be easy to study something that's so bright, but in fact, it's not. Um, I'd always worked at the other end of things, trying to strain the ability of the telescope I was using to collect enough light from the distant object. And here you have way too much light, and so it presents actually a very difficult problem that took my students and I about a year to accomplish the feat of being able to actually observe Betelgeuse using the equipment at our local observatory, known as Mount Laguna Observatory near San Diego. Um, but it turned out that the timing of kind of coming online with our own study was very fortuitous, because just as we were coming online a little over a year ago at this point, Betelgeuse started doing something that got a lot of people's attention. It was behaving funny or strange. Um, and the headlines inevitably began to suggest that something very dramatic even was about to happen to this star. And through the end of 2019 into January of 2020, by month's end, it was kind of reaching a fever pitch. I mean, people were even prescribing potions to protect you from this event that was going to happen. But why was there all this excitement? To understand why people got so excited about a year ago, you just have to go back about 1,000 years ago to July 4th of the year 1054 AD. And I'm going to show you a little clip of Carl Sagan uh, uh, imagining what that night might have looked like. And I don't know if I think the sound isn't going to be too loud here, but you'll get most of it from the visuals anyway.
Imagine the night when that colossal stellar explosion first burst forth. A 1,000 years ago, people gazed up in amazement at the brilliant new star and wondered what it was.
Stars do explode. And if one as close as Betelgeuse is actually exploded, it would simply be amazing. I mean, suddenly replacing Betelgeuse, and this is an artist's rendition of what we might see, would be a point of light that would be about as bright as the combined light of the quarter moon in our sky. It would be clearly visible during the daytime, casting its own shadows in the nighttime. But how did we get to this point? Why were astronomers getting so excited about this famous star? And why hasn't it happened already? Obviously, it hasn't exploded yet. And just when might we expect it to explode? I'm going to give you tonight the best answers that we have to these questions. And it starts by letting me remind you of where we are in the universe. Our sun, the retinue of planets going around the sun, is not alone. We sit inside of this vast stellar system known as the Milky Way galaxy, which contains over 100 billion stars that are just like our sun, all bound together gravitationally. Our sun sits somewhere out about here, very far away from the center. It orbits the center of our galaxy once every 250 million years. And you've probably noticed that this isn't a picture, this is a portrait or an artist's rendition of what our galaxy might look like, what the Milky Way might look like. And the reason for that is we've never sent a spacecraft far enough away to get out of our galaxy and turn around and take a snapshot of it. Not even close. Distances in astronomy are just so vast, and we actually measure them in terms of how long it takes light to reach from one place to another. And to give you a sense of just how big our home galaxy is, let me start really close to home with the moon. It's the closest thing to us. It's the only place we've actually gone other than the Earth, and it's shining by reflecting the light given off by the sun. It's only about 200,000 miles away, And it turns out that light travels about 200,000 miles every second. And so what that means is when you're looking at the moon, you're seeing light that has taken about 1 second to bounce off its surface and then travel the distance to reach us. You're looking back in time about 1 second when you actually look at the moon. So astronomers might say the moon is 1 light second distant from us. The sun, like every star, is a self-luminous ball of very hot gas. Unlike the moon, it gives off its own light. It generates its own light. It's about 500 times further away from us than the moon is, and if you do the math, that means the sun's light takes about 8 minutes to reach us. So you might say the sun is 8 light minutes away from us. And astronomers have learned that our sun is just like all those other stars you see in the night sky, but so much closer that it drowns out all of the stars of the celestial sphere during the daytime. How much closer is the sun than all these other stars? Here's a picture of the closest star to us, known as Alpha Centauri, and it takes Alpha Centauri's light about 4 years to reach us. So when you look at the closest star in the night sky, you're looking back in time 4 years. It is 4 light years away from us. When we return to this whole collection of stars, over 100 billion stars that make up the Milky Way, you can see why we've never traveled outside of it to get a picture. From end to end, the Milky Way is about 100,000 light years across, and we're about 30,000 light years from the center. The most distant spacecraft ever launched by humans, Voyager 1, launched in the late 1970s, and traveling incredibly fast, is still less than 1 light day away from Earth. So we are far from getting outside of our own galaxy. That said, sitting out here, we have a great perch to look at the rest of the universe. And when we do, we find that it's littered with galaxies, like our Milky Way, billions of them. And each galaxy has upwards of 100 billion of its own stars. The closest major galaxy to us is known as the Andromeda Galaxy. It's roughly 2 million light years away, and you can actually see it with your own eyes if you know right where to look. This is a photograph of Andromeda taken with a good camera, and here is a photograph taken with a telescope by an amateur astronomer. It's the closest major galaxy to us, and as we look further and further away, we just see billions of these galaxies. And our clearest pictures of these galaxies, taken with the finest resolution, capable of resolving even some of the brightest individual stars in them, if they're close enough, using the Hubble Space Telescope, this orbiting observatory that's launched over a quarter century ago, taking the most exquisite images we have of the sky. Since it sits above our atmosphere, it takes the crispest pictures of other galaxies. Let me just show you some of the pictures it's taken. Here's a beautiful galaxy containing upwards of 100 billion stars. Here's one of my favorites. So if you think about it, if each one of these galaxies contains roughly 100 billion stars, I'm now going to tell you that having a star explode in a galaxy is actually a quite rare occurrence. It's rare because stars only explode once if they're going to explode. It's also rare because not every star ends its life that way. Our best estimate tells us about 1 out of every 400 stars that nature mints will live a life and then die by exploding. So that sounds pretty rare, but if you think about it, if there's 100 billion stars in a typical galaxy, and if you work out the odds that there are 100 billion visible galaxies in our observable universe, you can kind of figure out that you're going to see exploding stars all the time in our universe. In any particular galaxy, maybe 1 per century goes off. But in our visible universe, about once per second, a star is exploding. We don't capture nearly all of these, but these days we do discover several thousand exploding stars every year. Let me show you a picture of what an exploding star looks like in another galaxy. So this is a famous galaxy. It's called the Whirlpool Galaxy. It's located about 23 million light years away. This is a picture taken in early 2011. Galaxy was just happily minding its own business. And just to really impress upon you, what you're looking at here are really two things. These dots here, these are stars in the Milky Way, maybe 10 light years away, maybe 100 light years away. Plastered against that in the same field here is something 23 million light years away, the unresolved light of over 100 billion stars in the Whirlpool galaxy. So don't be confused by the foreground stars. You're looking at the universe through a screen of stars in our Milky Way. One day in 2011, one of its stars decided to explode. And what this is going to look like is a brand new, very bright star appearing in this galaxy. And so what I'm next going to show you is a picture taken after the explosion. See if you can spot the new star in the new image. If you don't see it, it helps if I blink the images. So here's the before picture, and then here is the after picture. Before, after. Right there is the supernova. And at that distance, 23 million light years, that's a really bright star. It's rivaling the brightness of these stars in our Milky Way. Probably about 1 billion times the luminosity of our sun at this point. So if we see these things happening all the time in other galaxies, why so excited about Betelgeuse exploding? It's only 500 light years away. And it's exactly the kind of rare star that we are pretty sure will end its life by exploding as a supernova. The type of star Betelgeuse is known as a red supergiant. Red because it's red. You can really see that when you look at it in the sky. And supergiant because we figured out that it's a humongous star. In terms of size, if you were to take Betelgeuse and replace our sun with it, it would swallow up all the terrestrial planets, including Earth, and reach all the way out to Jupiter in the solar system. That's how big this star is. It's also very heavy, very massive. We estimate it has about 20 times the mass our sun does. And that's very rare. Nature doesn't make too many of these behemoths. It's also extremely luminous in terms of luminosity. Right now, it's giving off about 100,000 times more light than our sun does. Only 1 in 400 stars ever achieves the state Betelgeuse has, and poised to explode. How do we know this is what's going to happen to Betelgeuse? We've seen it happen. In the last couple decades, we've now seen stars that look exactly like Betelgeuse in other galaxies explode. Let me show you some pictures of how we know Betelgeuse is about to explode. This is a supernova from the year 2008. Here's the host galaxy, this fuzzy blobby thing down here. And this point of light there, that's supernova. It's known as 2008 BK. It's one of the closest supernovae of the last decade. It's only 13 million light years away. And down here is an extreme close-up of the region right around supernova 2008 BK after it had exploded. The good news is astronomers before the explosion had actually imaged exactly this part of the sky at very high resolution, so that after it exploded, we were able to go back and look at pictures taken before the star had exploded. And these two pictures I have up here were taken at different resolutions and through different filters. This one, the before the supernova, was actually taken in many filters, so we were able to make a color image of the field. This one is just a single filter image and is at higher resolution than this one. But you can start matching the stars up. That star is this star. This star is that star. This one is that one. You can line them up. And when you match up the photographs really carefully, you find that sitting right at the location where there's now a supernova is a bright red star. This is what we call the supernova progenitor. And guess what? It looks exactly like Betelgeuse. It's the same color, it's the same luminosity, it's the same temperature, it's the same size. It's exactly a kind of star we know explodes because we have these before and after pictures now showing that it did. And in case you're skeptical that that star actually exploded, and a long after picture reveals that the star is now gone, which it has to be if it blew up. So convincing evidence that red supergiants explode as supernovae. And so one day Betelgeuse is going to do this. We're rather certain about that. Before embarking on a study of Betelgeuse itself, this is the kind of work that I did. It's kind of like stellar forensics, going back in time and looking through archival images to learn about what are called the progenitor stars of supernovae. Pretty painstaking work, and these objects are all millions of light years away, trying to derive characteristics of the stars and convince us we know what kinds of stars are in fact exploding. We kept finding red supergiants, the same kind of star Betelgeuse is. We have very good observational evidence then that Betelgeuse is definitely going to explode. Question is when? When is the big event going to happen? And why did people get so excited about a year ago? For that, we have to kind of delve into the heart of the matter. And I say the heart because the thing that triggers the explosion of one of these stars happens deep within the core of the star. What's happening on the surface is just some kind of delayed indication of what may be happening in the core. And so let me tell you the story of just why we think stars explode. And this all begins with understanding how a star lives. If you want to understand how it dies, you got to know how it lives. And the way I like to think of a star's life is a kind of a fundamental war being waged between opposing forces. On the one side, you have gravity, always trying to compress things, always pulling things together. A star is a hot ball of gas. Gravity is trying to crunch it down and squeeze it together. It always wants to compress it, all right? But while a star is living, there's an opposing force pushing out against gravity and keeping the star puffed up. And essentially, that force is the force of light itself. Light itself exerts a pressure, and it pushes out against the outer parts of the star and keeps it in equilibrium. Deep in the core of the star, there's a tremendous energy generator producing all this light, which keeps the star puffed up. So think of the star as a battle, gravity in, pressure out, and during the normal phases of life, the star stays in a nice equilibrium state. The energy generator, the source of the energy, which was first worked out in the 1950s, is hydrogen for most stars, the simplest and most abundant element in nature. And that's good, okay, because when our universe began about 14 billion years ago, there was just hydrogen and not much else. And so stars are basically big balls of hydrogen gas. And hydrogen is the simplest element, has just one proton in its nucleus, and it sits here atop the familiar periodic table of elements. And what's happening in the core is that hydrogen nuclei, basically protons, are whizzing around so fast because it's so incredibly hot in the cores of these stars that occasionally two protons actually overcome their electric repulsion for each other and get so close together that they fuse together and ultimately form the next element of the periodic table, which is helium, which has two protons in its nucleus. And whenever this fusion happens, a little bit of light is produced. And when billions of atomic nuclei are doing this every second, a lot of light is produced. And that's the secret. In the cores of stars, light elements are being fused into heavy elements through this process we call nuclear fusion. And it creates the light that pushes out against the outer layers of the star and keeps it puffed up. The problem is, at some point you run out of fuel, you run out of hydrogen. And elements heavier than hydrogen, like helium, can fuse, but they require even higher temperatures to get those more protons close enough together to fuse into things that are heavier. Um, so once the core is done with hydrogen, it's got to work on helium. And for stars like our sun, this will happen. It will go to a new round of fusion and produce elements like carbon and oxygen. And in this way, steadily build up these heavier elements. But a funny thing happens if you're worried about our sun. After it's done fusing hydrogen to helium, which it's currently doing, and then ultimately helium into carbon and oxygen, after that, it's done. It can't fuse anymore. And the reason it can't is that the core never gets hot enough to fuse heavier elements. And the star will then die in a very graceful exodus from our universe, where it just puffs off its outer layers into interstellar space. The core compresses, shrivels up until it finds a new force to stop it. And that only happens after it's shrunk down about a factor of 1,000,000 in size, down to something about the size of the Earth or so, until a quantum mechanical force, where resulting from electrons not liking to be close together, stops the compression, and you wind up with this dead corpse of a star made out of carbon and oxygen that we affectionately call white dwarfs. That's the fossil fate of 399 out of every 400 stars that nature mints, and it's the fate of our sun in about 4 or 5 billion years. We see thousands of white dwarfs littering our galaxy. But you'll notice this is a picture, I should say, of a star becoming a white dwarf and puffing off its outer layers into space. They're beautiful to look at. But nowhere in here is there an explosion. It's a pretty gentle process. To get an explosion, you have to pick a star that's born with more than 8 times the mass of our sun, and that's very rare. The reason you need more than 8 times the mass of the sun is that only stars that are that massive can generate temperatures hot enough to fuse elements heavier than carbon and oxygen. And I should say that when these very massive stars are fusing even helium into carbon and oxygen, they do so at such a prodigious rate that that war between gravity in and pressure out gets won by pressure out for a while. And when the star is done fusing hydrogen in its core and starts fusing heavier elements, it actually bloats up. It becomes a gargantuan star because of this pressure imbalance. There's more light being produced than gravity in a sense, and it pushes the star's atmosphere out, and you get this gargantuan star. And that's what you're seeing when you see a red supergiant. You're seeing a star very near the end of its life, a high mass star. And so Betelgeuse at least is in that phase. It's in the phase of fusing helium into carbon or oxygen. And so when you see a star bloated up as a red supergiant like that, like Betelgeuse, you know it's coming near to the end. Unlike the case for the lower mass stars, though, when carbon and oxygen are formed in the cores of these high mass stars, it doesn't stop there. The core temperatures are so hot, they're able to fuse further. In fact, they're able to fuse elements all the way up to iron on the periodic table, 26 protons in the nucleus. And at that stage, you have this really complicated looking structure to a star. There's a huge, we call it the envelope of hydrogen, but then deep in the center is this tiny core where you end up with all of these heavy elements, the ashes of the previous rounds of nuclear fusion, building all the way up to an iron core in the center. But once that iron core develops, nuclear fusion's dead as a fuel source. And that's just a rule of quantum mechanics. You can't get more energy out of fusing elements heavier than iron. And so the star's fate is then sealed. But unlike in the gentle case for the low mass stars, what happens next is very violent. When the iron core reaches probably about 1.5 times the mass of the sun, the mass is just too great, and it just implodes. It collapses catastrophically. In less than 1 second, it goes from something about the size of the Earth down to something maybe the size of Trenton or Atlantic City. I'm not sure of the sizes of these cities, but something like 10 kilometers from one side to the other. And in that collapse, the protons and electrons essentially get squeezed together to form neutrons, and you basically just have this ball of neutrons collapsing. It eventually halts when the quantum mechanical pressure resulting from neutrons getting squeezed too close together takes over. And you have the birth of what's called a neutron star at that point, just a ball of neutrons essentially. The rest of the star, no longer supported by that core, implodes on top of this. And what happens next? Well, we know what happens next. All of that material smashes into this newborn neutron star, a shock wave forms, pummels its way out through the envelope, and ejects it out into space. This is what we call a supernova, announcing itself with a brilliance that for a time is over 1 billion times the luminosity of the sun. And this is exactly the fate that awaits Betelgeuse, just like it does every red supergiant. The problem is the timing of the event. We know by virtue of the fact that Betelgeuse is a red supergiant, it's done fusing hydrogen in the core. But that's about all we know. The problem is it can fuse helium for about 1 million years, looking just like this. Okay? The rest of the stages go by very quickly. If it's fusing carbon in the core, it's got only about 2,000 years left in its life. If it's fusing neon in the core, and you can see these letters here, it's got about 6 months. And if it's fusing silicon in the core, it's only got a couple days left. If we could only see the core of Betelgeuse, we'd have our answer, but we can't. We only see the surface. And so we get very excited when strange things start happening to the surface. And that's exactly what happened about a year ago. Let me tell you the story here. Being about the 10th brightest star in the sky, Betelgeuse has been watched for thousands of years, and it was first noticed back in the 1800s that it seemed to vary in brightness. It didn't stay constant. And for the past 100 years or so, we've been keeping careful track of how bright Betelgeuse is in the sky. And I'm going to show you it's called a light curve of Betelgeuse. It's just a plot of how bright Betelgeuse is versus time for the last 7 years or so. And here it is. Okay, so if you see what we've got here, this is the brightness of Betelgeuse. Each data point here taken by an astronomer, how bright Betelgeuse appeared to them. Typical brightness indicated here. Half as bright is down here. And the year starts at 2013 and ends up here at 2020. And you can see there's a cadence to the ups and downs of Betelgeuse, okay? Dips and peaks, and that's quite a bit. You'll also notice that there are these gaps, okay, every year at about the same time. What do you think that is? That's the sun being in the way. Betelgeuse goes behind the sun. We can't see it, so we get no data during those months. All right, that's why there are those gaps. But you'll see that I chopped off this last period leading up to 2020 up here. So let me show you what got everyone's attention at the end of 2019, and that was this. Betelgeuse just started plummeting in brightness. I mean, way dimmer than anyone had ever observed it getting before. In fact, all the way down to about a third its normal brightness in the sky. I mean, you could just go out at night and look, and if you were used to looking at Betelgeuse, you would see it's obviously very dim. It went from being about the 10th brightest star in the sky to about the 30th when it was at its dimmest. And this is what's led to all the rampant speculation that this might be a signal that it's about to explode. I even noticed it reached New Jersey as well. I got excited about it in New Jersey as well, as other places. And it went on into January and into February. Astronomers have learned to be very patient, though. The press is not so patient. Okay, I really liked this particular headline. biggest cosmic explosion since the Big Bang spotted in distant galaxy. No, sorry, it's not Betelgeuse. um, when's this thing gonna explode? See, the problem is trying to predict what's happening in the core based on unusual behavior on the surface. Just because the surface was dimming, is that really telling us anything about what was happening in the core? The theory is kind of maybe on this. These stars are so big that any change in the core would take at least hundreds of days to make it to the surface layers and affect those at all. Um, and it's not clear that nuclear fusion changes in the core should affect the surface in the way that was being seen. Um, Nonetheless, it was exciting, and it definitely did encourage astronomers to try to look to the historical record to see if such dimmings of red supergiants might precede supernovae. And a few astronomers did this search. They actually found uh, uh, four supernovae of the type that Betelgeuse is presumed to be, and they had archival images, and they looked. Did the star dim notably before the actual explosion? And what they found was no. Uh, they found the stars to be quiescent, no significant evidence for stochasticity or steady variability. So it sort of seemed like this wasn't like a warning of an explosion, and so it started casting doubts on the idea that it was going to explode. And by May, the press kind of had enough, but there was still clickbait for people who were interested that Betelgeuse might be exploding. But reports of the imminent demise did get tamped down, especially when Betelgeuse's light curve returned back to its normal brilliance in the sky. So this is kind of the final scene here where it's come back up from that historic minimum um, and back up to its normal brightness. If you're wondering what it's been doing since then, I just today downloaded the light curve for all the way up to today. It's just piddling around at about its normal brightness, not doing anything too extraordinary. But the question remains, just when will it explode? Turns out that one of those last articles I wrote you after the catchy headline did get it right. And it's good they got it right because they interviewed me for the article. And so you can see now that it says any day now or night, the red supergiant is expected to explode and go supernova. Any day that is within the next 100,000 years or so. I'd actually be even more conservative than that. And if I were to hazard a guess and give a real range for our uncertainty, I would say sometime in the next million years. If you really forced me to give a precise answer, I'd say it's probably most likely to explode in about 100,000 years. And this is based on some surface chemical analysis that some astronomers have done that give some clues about the stage of life it's probably in. But unfortunately, that's about the best I can do for you. Keep watching it. It wouldn't surprise me at all if it blew today, which would mean it actually blew up 500 years ago, right? But we can't pin it down much better than this at this point. This does leave us with the mystery of what caused this incredible dimming that we see for Betelgeuse. I mean, what causes all of the variability we see for Betelgeuse? Don't really know. Stars of this ilk are known to pulsate, experience radial pulsations, and big convection cells on their surface, giving rise to enormous sunspots, basically, star spots. And there's a periodicity also seen to this. And so it's widely been believed that it's some kind of pulsational cycle. But why did it go much dimmer this last time, this unprecedentedly faint dimming here? Let me show you an interesting possible clue that was provided by an amazing observational technique that actually enables us to resolve the surface of Betelgeuse and image it. And that's by virtue of the fact that it's so big and so close. It's one of the only stars for which this technique gives you a successful result. And I'm going to show you two pictures. The first one is taken back in January of 2019, and then the next one about a year later. So seeing if there's any big difference between when it was kind of in its normal state versus when it was extremely faint. And here's the first picture. So you're actually seeing a resolved image of the surface of Betelgeuse. It looks like a star. I just point out again, if this was the sun, Jupiter would be out about here, orbiting within the outskirts of this bloated red supergiant. But let me show you the image taken about a year later, December of 2019. Look at that. Uh-huh. Um, it appears the southern hemisphere of Betelgeuse dimmed. Why did that happen? It kind of admits two possibilities. These are the two that have survived to today. The first idea is that a portion of the surface of the star could be getting much cooler. The temperature may have gone down at the surface. And basic physics says if you have an opaque gas and the temperature is lower, you get less light emitted. We know big stars like this have huge convection cells. Maybe some kind of enormous sunspot temporarily appeared on the surface of Betelgeuse. The second idea, and the second idea is that something could just be blocking our view. And in astronomy, the thing that most often blocks our view of background objects is something we call dust. Little tiny grains along the line of sight to an object, having zillions of these little tiny grains collectively dims our view of the thing coming from behind it. We know stars occasionally will kind of belch out a lot of gas and dust and temporarily become very bright or very dim because of this experience. The most famous star that ever did this looks like this today. This is a star known as Eta Carinae, which in the 1800s kind of just had this enormous eruption, where now we see all this dust formed, blocking our view of the gargantuan star buried inside. No one thinks anything that dramatic happened to Betelgeuse, but maybe it just sort of erupted a whole lot of this dust, and that's obscuring our vision. So we kind of have these two ideas. Maybe the surface temperature dropped, just like it does in any sunspot on our sun. That's why it looks dark. Or there's dust blocking our view. And this is a raging debate. It's playing out in both the scientific press and the popular press. I'll show you a few articles from the scientific press, some on the side of dust causing the dimming, others on the side, no new dust required, photospheric temperature, that's the surface temperature of Betelgeuse during the Great Dimming, is what caused it. And then, of course, that gets followed by, no, it's not the surface temperature, it's dust, okay, that's causing it. And then some commentaries just sort of have funny titles like this. Betelgeuse is fainting, not hypothermia. It didn't get cold, it's dust. Popular press follows this and, is usually a little more definitive than the actual scientific articles, claiming, it's either gigantic star spots, it wasn't dust, or claiming, the bright stars dimming may have been a big dust burp. It kind of goes back and forth. And so, which is right? Is it dust or is it temperature? I'll just say the jury's still out on this, but at the risk of getting very geeky here right at the end of the talk here, I'll just give you a hint at the work that my group's doing. Mainly a student, Bobby Baldocci, and I are working on together, that may lead us to some conclusions about which side we're going to come down on here. We're still analyzing these data, but it starts really fortuitously back last January when, after wrestling for over a year with our telescopes, we were able to get what's called a spectrum of Betelgeuse. I can't tell you how hard this was to get, but here it is. And let me explain sort of what you're looking at here. Isaac Newton taught us that when you pass light through a prism, or any substance really, it disperses it into all of its colors or wavelengths. You can then, if you're very careful about what comes out the other end of the spectrum, you can make a plot of how bright the object is at every wavelength or every color. So I could, if I wanted to, replace these scientific appellations for the X and Y axis of wavelength and flux with color and relative brightness. That's really what a normal human being would see. And you're seeing how bright the star is at every color of the rainbow. And not surprisingly, first of all, you see that the star is very bright at red wavelengths and much dimmer at blue. That's why it's red in the sky. It gives off much more light here. All right. But what we're really analyzing here is all of these features in the spectrum, these ups and downs. These are real, and they can be identified with absorption by particular chemicals, particular molecules in the atmosphere of this star. And in particular, these TiO bands, these are called titanium oxide bands. The strength of these bands is a sensitive temperature indicator of the surface of Betelgeuse. Here's 3 spectra that we took, going down to the historic minimum. And these subtle changes in the strengths of these lines are the things that my student and I are trying to calibrate really carefully, and then trying to tease out what it's telling us about either temperature or dust. What do I think at this point? Temperature. I'll come down on that side. But what do I know? Nothing. We're still analyzing these data, and we're still collecting as I speak. You'll just have to stay tuned on the answer to what caused that historic dimming. So let me just conclude. Bottom lines here. When will Betelgeuse explode? Sometime in the next million years. If I'm a betting man, I'd say about 100,000 years. Start looking really close, but it could be tomorrow, so just keep looking. Why did it dim? We don't know, but we do have ideas. Invite me back in a year, and I'll give you the status report then on what we think about Betelgeuse's historic dimming. Or if Betelgeuse has actually exploded by then, you won't really need me to fill you in on that fact. And so with that, I'm going to conclude the talk, and thank you very much for your attention, and I'll be very happy to answer any questions that you have about Betelgeuse or anything else.
All right. Thank you so much for the talk. It was very great. I do actually have one current question in chat. It says, how long do you think the star would brighten up the night sky once it did explode?
Well, that's a great question. If it's a typical supernova of the type we think Betelgeuse will be, this is how it will behave. First of all, let me just stress, to your eyes, it will just be a dot. Okay, you're not going to see this explosion. Even a supernova 500 light years away is still just a dot to your eyes. You need very special telescopes to resolve it. A typical supernova like Betelgeuse has a supernova has a light curve that does the following. It rises very quickly. So over the course of maybe a week, it rises in brilliance. You'll see it just getting brighter and brighter and brighter and brighter. And then it'll hit kind of a peak. And a really neat thing will happen at that point. First of all, you'll be able to see it in the daytime, even if the sun's out. Okay, so whatever time of year this happens, we'll know. Okay, and then you ask, how long will it stay? Well, for about 100 days, this kind of supernova typically stays at exactly the same brightness. It's a really interesting phenomenon that keeps it at about the same brightness, so about the brightness of the quarter moon or so, for about 100 days. It'll just shine brilliantly in our daytime and nighttime skies. And then it will fall in brightness a lot, by maybe a factor of 3 or 4 in brightness. It'll fall very rapidly in brightness. And then for years, we'll just watch it slowly get fainter and fainter and fainter. And then after several years, it will have dimmed beyond what we could even see with the naked eye. But with telescopes, we'd be able to study the supernova for centuries.
All right. A follow-up question on that. Would it be visible during the daytime?
Yeah.
Or is it okay, so it will be visible during the
Yeah.
daytime.
I
All
mean,
right.
if it's all of this has an asterisk, and that asterisk is we think we know there are several types of supernovae. We're pretty sure Betelgeuse will be of the type that I'm describing, but astronomy has a nasty way of surprising us. And I've also noticed that the closer an object is, the more surprising it tends to be. It's just something interesting about astronomy. But if it's the kind of supernova we think it will be, it'll be easily visible during the day. I mean, just think of the moon. You can see the moon during the day, and Betelgeuse will be as bright. It'll be the concentrated light of the corner moon all in one dot. So it will be very bright, and it will cast shadows at night, just like the moon does.
All right. How long does a red giant typically live?
Depends on its mass. These are great questions. Um, so you probably know our sun has been around for 4 or 5 billion years. The amount of time a star lives, kind of counterintuitively, um, is inversely related to its mass. That means the more mass the star has to begin with, the shorter its life. It would kind of seem it should go the other way. The more mass, the longer, because it has more fuel. But it turns out the more mass a star has, the faster it uses up all of its fuel. It burns really bright and it dies really quick. And so stars like our sun last for billions of years. Stars like Betelgeuse only last for millions of years. And the longest that a star can live that will die by exploding as a supernova is 40 million years. And that's for a star that's right at about 8 times the mass of our sun. A star like Betelgeuse, probably talking more like 10 million years for its whole life. And that sounds like a long time, but in astronomy, that's the blink of an eye. And so, probably about 10 million years. It's at least through 9 million of those years at this point because it's now in this bloated stage that it only gets to at the end of its life. But that end can last another million years. That's the uncertainty.
All right. What can cause these dust burps or emissions from the stars?
Great question. No one knows. We see these things happening, and it's a question of what kind of an instability is happening in the interior of the star that leads to such an ejection. Um, and we have theories, some pretty exotic, but nothing proven at this point. We know that the highest mass stars, that picture I showed you of Eta Carinae, is probably like a 100 solar mass star. And it's kind of speculative what causes those kind of enormous eruptions. Something called apparent instability inside is a leading theory. But bottom line, we don't really know. We see these things happen. We know they happen to very massive stars. It's possible Betelgeuse did this. A lot of it can be related also to something called convection in the outer layers of these stars. You have hot gas trying to surface over cool gas, and this can sort of happen in an eruptive kind of way. The other thing you'll see a lot of discussion of when it's talking about these eruptions is magnetic fields. And whenever you see astronomers talking about magnetic fields, it means they don't really know what they're talking about because no one understands magnetic fields in stars. But that's what causes star spots, is kind of magnetic fields getting twisted up in the surfaces of these stars. So this is a long way of saying I wish we knew what caused these eruptions, but at this point we just have some theories.
All right. A Another fun question. Where did the name Betelgeuse come from?
Oh boy. I should I've heard I'm gonna have to say I'm gonna have to claim ignorance on this, but I'm almost sure one of the viewers may know the answer to that. Because
I
I think I heard the story when I attended a star party, and this is the kind of thing professional astronomers don't know, but amateurs often really know these kind of things. I don't know where it got its where it got its name. If someone does, please chime in, or you can just
uh
Google it.
I believe I actually do have an answer, and people feel free to correct me because I'm going off of memory of a different presenter's presentation. One of our presenters, Lonnie Bunis, who actually did our last presentation, has talked about this before. But we've had people naming stars for ages. There are like Arabic and whatnot, and I'm fairly certain that he said that Betelgeuse was Arabic in nature,
That
and
much I know.
I believe it literally translates to something like the giant's armpit,
Okay, that would make
um,
sense.
where some people have taken liberties with translation, as you often do with translation, because sometimes a direct literal translation doesn't make quite as much sense or eloquence as if you take some leeway.
Yeah. So yeah, that sounds. I mean, this is the historical name for the star, and I'm trying to get back and yeah, and this is Orion the Hunter, and there sits Betelgeuse right in the armpit of uh of Orion, right?
And so someone has just corrected me that it is Arabic for hand, which,
Maybe they saw a hand. Different cultures saw different things with these.
yeah.
Oh, that's a good question.
I actually have a fun question because in your bios it said you uh, had studied black holes, correct?
Sure. Yeah.
I a previous viewer had brought up the topic of what is a white hole. Is there a short
Yeah.
definition, or is that even a thing? Because that was the first time I had heard of it.
Yeah. So okay. So let's start with what a black hole is. A black hole is uh, uh, a I'll say it's an allowed thing in Einstein's general theory of relativity, which is the theory of gravity that we have today. And what it says is that if you take enough mass and compress it down to a small enough volume, the equations say no force in nature can stop. Remember, I said gravity is always trying to compress things. Well, if you get enough mass together in a small enough volume, there's no force possible that can actually push out strong enough against gravity, and it will collapse the object down to a point. And so you wind up with this point that has mass but zero size. It kind of makes your head hurt. But that point is what's called a singularity. And you can calculate there's a region, if you get too close to that point, the gravity is so strong that not even light itself, which travels incredibly fast, can actually escape from the thing. And it's that region, the singularity bounded by a region called an event horizon, beyond which everything's trapped. Everything's doomed to fall into the singularity. And it's this object that we call a black hole. It basically doesn't let anything out. Okay, anything that gets in just falls in. Um, Einstein didn't believe in black holes. He didn't think they existed in our universe. And for decades, we had no proof that our universe actually made such things. But beginning in the early 1990s or so, the evidence has gotten very convincing that nature actually mints black holes. One of the ways she does it is in this collapse of a high mass star that I described. Instead of ending up as a neutron star, if there's too much matter, it can actually snarf down into a black hole. Um, so nature does make black holes. Einstein's equations work, eh, to put it simply, they work in both directions. Um, his equations allow for the production of an object that doesn't let anything out. They also allow for the production of an object that doesn't let anything in. They're totally reversible. It's legal, in other words, meaning they allow for the existence of an object that nothing can stay near. Everything just gets ejected from this object. And that opposite of a black hole is what people have termed a white hole. And as far as we know, our universe doesn't produce these things. We don't have any evidence that white holes exist. But they're just the reversal of a black hole in the mathematical equations of general relativity. And one of the lovely science fiction ideas is, what if you had a black hole where everything falls in, somehow connected to a white hole where everything gets spit out? And the connection thing is what's called a wormhole. And it's this way that might allow something or someone to transport from one place in the universe to another very quickly. So white holes, not disallowed by general relativity, but no evidence, no convincing evidence, I'll say, that our universe actually mints them, actually produces them.
So basically, math says yes.
Math says yes.
In practicality, who knows?
Who knows? Yeah, I mean, the moment the math says something's not illegal, it definitely leads you to want to find these things. I mean, that's what led to the search for black holes, because the math said they could exist. It's up to nature whether she chooses to produce such things, and all we can do is look for them. But at this point, no evidence for white holes.
Right. So it looks like we are currently kind of out of questions. I want to thank you again for such a great presentation, and thank you for sticking around to answer our questions. And I
Sure.
want to thank our audience for joining us during this presentation. Um, Remember, please hit that like and subscribe button if you want to hear more live stream goodness. Please look us up on our social media through Facebook, Instagram, Twitter. You can look at through our website also, UACNJ.org. Please do check us out. We are a nonprofit, so all of our programs are supported by donations from people like you. We do have information on our member clubs, where we are located, when we might get back to our physical in-person presentations, and also if we would be holding any special events on our website. Oh, it looks like there is one more question, and I'm just grabbing that out real quick. Someone asked, in reference to the gaps in the Betelgeuse light chart, how many days per year does the sun block the view of Betelgeuse?
That's a great question. And I think the answer is it depends how risky you wish to be with your telescope. How soon after sunset or how close to sunrise do you want to point your telescope and risk that you point at the sun? It's approximately, I'm trying to think, our last observation of last spring was at the end of April, and we really pushed it. It was right after sunset, and in the haze of twilight, we were able to get a spectrum. And that was about April 30th, April 25th, I think. And then it comes around to again be visible in the early morning hours, right before sunrise, about August 20th or so. So let's see, that's basically May, June, July, so that's 90 days. I'm going to go with something like 115, 120 days. It's blocked. And you can see this in these gaps. That's consistent with what you see here. The annoying.
I'm sure there's a more detailed chart that you could probably go find.
Yeah, it's going to be something like that, though. Something like 100 some days.
All right. And like I said, I want to thank you again. I want to thank our audience. Thank you for that last question. And I will see you next time that it is astronomy time. Have a good night.